We'll see if it holds. And then 22.4 liters is 1 mole. Everybody remember that? Okay, and that's how you would do that. And you would do that because you know you're at STP, because you know you're looking at a gas, we can make the assumption, or not really, we can use the equality 22.4 liters is 1 mole, okay, for your neon gas. Make sense? Okay. And in this whole gas law thing, I complained and railed that we shouldn't be doing that we should instead be using PV equals nRT. Since we were solving for the number of moles, I just need to get moles by itself. So PV over RT, right? Okay, and this is a lot more work. Okay, we were given volume above, so I'm just going to pull the volume out separate, and then we have P over RT. Everybody good? Okay. So what we've got is the same general format. 2.34 liters is our volume, so there's our volume pulled out. And then we multiply by some conversion factor, which is this guy. Okay, so I just want to look at what is P over RT. Okay, so just P over RT. What is P?
Pressure.
Pressure. What is the pressure?
1 atmosphere.
Because we're at standard temperature and pressure, we know we're at 1 atmosphere. What is R? That's a fair statement. It's our gas constant. Right? If you have to move into 151, they'll push this a whole lot more, and you'll see a lot of PV equals nRT. We don't see it quite as much. Okay, it's our gas constant. It is 0.0821, and this is where it gets nasty. Liters times atmospheres over moles times kelvins. That all nice and neat in parentheses.
That's our R.
That is our R. That whole thing. Okay. So I can already understand why you're like, I don't want to memorize. I understand. Okay? But I want you to at least see where this is coming from because it's important. If you have to move into 151, you have to use that. There's no cheap shortcut to it. Okay? And then times our temperature. T. What was our temperature? 0 degrees Celsius. Take a look at our gas constant, though. Okay, our gas constant uses liters, atmospheres, moles, and K is Kelvin, so we have to be in units of Kelvin to make this equation useful. So if we're at 0 degrees Celsius, that is 273 Kelvin. Okay, so far so good? So all we do is just jam some numbers in. Okay, so atmospheres is in the numerator, atmospheres is in the denominator. So those can cancel. Okay? Kelvin is in the numerator of the denominator. Everybody catch that? Some people are like, yeah, I get that. Does anybody be like, I have no idea what you're talking about. How can you be in the numerator and the denominator? You're just not going to volunteer, say, I'm confused by that? You're confused. Okay, let's take a look at this. Okay, real quickly, or attempt to be real quickly. We're used to saying a fraction, right? Numerator, denominator. Okay. Could I have a fraction in the numerator? Okay. I could have a numerator. I could have a fraction in my numerator. Okay. Numerator 1 over denominator 1 is the numerator. Okay. Could I have a fraction in the denominator? Yep. So I could have numerator 2 over denominator 2. This whole piece here is the denominator. This whole piece here is the numerator. Kind of, sort of? Okay. So when we go through to look at the gas law system that we've got here, we have a fraction, liters times atmospheres per mole times Kelvin. So I do have a fraction in the denominator. Where is the Kelvin for our temperature located? In the denominator. Is it in the numerator part of the denominator or the denominator part of the denominator?
The numerator.
The numerator part, so the Kelvin's units can cancel. Everybody see that now?
Yeah.
Okay. I think we even heard some choice words too. Exciting. Okay. So now let's move to the next fun part. I still want to mess with the units. So if I look at the units, so what is in the numerator? What unit is currently in my numerator? Is atmospheres in the numerator? No, there's nothing unit-wise in the numerator. What's in the denominator? Liters over mole. Liters over moles. Whoops. Except, oh, yeah, right. Okay, and I'm going to have to put a 1 up there. I need something to mark that spot. Okay, well, what does that equal? Some people are good at saying this, some people aren't. So let's look at a numerical example. If I take 1 over 2, what is 1 over 1 over 2? Okay. This is the same thing as taking this fraction and flipping it and putting it up top. So this is 1 times 2 over 1. What is 1 times 2 divided by 1? 2. Okay? So it's a mathematical thing on flipping fractions within fractions. So if we look at this unit, way to take it to the next step, what happens? This is 1 over liters over moles, which means that becomes moles over liters. Okay? So moles over liters. Everybody good with that? Okay. So now the part, I don't want to see that work there because now I want to deal with the number. So I'm going to erase all that. Yeah? Still good? Cool. Now let's deal with the number. What is the number in the numerator?
1.
1. Cool. What is the number in the denominator? 273 times 0.0821. Everybody see that? What is that number when we calculate that? Okay, good. I heard a calculator move. I appreciate that. If we do that, I mean, that's a hard one to do in your head. Carry, boom. I do that right? Yeah, that's pretty cool. Hey, how did I do that?
That's how we got that number in the first place.
You remember that stupid thing that I railed about and complained about all the time? That stupid conversion? Okay. That stupid conversion has a reason. That reason is Pivner. Okay? That's why it exists. Because, and I wish I had a better reason for this, but this is all I've got. Because most of the time, when we work with gases, we're going to run under the assumption that we would be working with them at 1 atmosphere. Well, if that's the case, then my pressure is a constant. It's always 1 atmosphere. Because R is a constant, I don't worry about that. Okay? So then, most of the time, when I'm working with gases, I'm going to say I'm going to work at standard temperature, which was 0 degrees Celsius. Right? Because that is a constant, I can now plug that in and set up all of those constants and jam them all together to make a new constant. That new constant is this expression. Right? So I have theoretically simplified the amount of work I have to do because I just said all of those things were constant. Right? Kind of makes sense? Do those assumptions make sense? No. Why not? How often do you work with gases? You don't. Okay. How often are they at 1 atmosphere? Rarely. Okay. How often are you going to do an experiment at 0 degrees Celsius? Never. So we're making the assumption that if I work with a gas, I don't, and it's at 1 atmosphere, rarely is, and I'm at 0 degrees Celsius, I'll never be there, then this expression is valid. And I can say 1 mole is 22.4 liters. Cool. Okay. When I win $1 billion, these are all the things I'm going to do. And I'm going to win that $1 billion in the lottery, where my odds of winning are 1 in some number that is massively huge. I'm more likely to get struck by lightning than win the lottery. Okay. Attacked by a shark in Arizona. Right? Making big plans don't make sense. The same kind of thing is happening with gas laws, or at least that expression. The gas law itself, Pivner, phenomenal. It is awesome. It is super flexible because I can put in the correct pressure, because I can put in the correct temperature. But this stupid 1 mole is 22.4 liters. Okay? It's kind of a neat hand wavy thing. Oh, look, we can make something look pretty. I can make something look pretty that doesn't look like chemistry. Okay? That doesn't mean it's useful. Okay? Kind of makes sense? So, I know I just complained and said this was the most horrible, awful thing that you should do. But in this class, we have these two methods to solve this question. And as painful as it is, that is what you are expected to do. Make sense? If you want to make me happy and smile, you could show all the other work. That'd be cool. But you don't have to. We good? Okay. So yeah, there's all that fun stuff. We already talked about that. The next big kind of part is looking at the relationship. So when it comes to gas laws, you're responsible for identifying the relationships between volume and temperature, pressure and volume, pressure and moles, pressure and temperature. You could use the ideal gas law, Pivner, to establish all those relationships. And in fact, when I go through and look at these things, that's exactly what I do. I go straight to Pivner, I rearrange them, look at the relationship between them, and say, well, what happens when I change one versus the other? If you instead want to just memorize each of the individual relationships, that's fine. Okay? So what do I mean by those relationships? What is the relationship between volume and temperature? What happens if that's the wrong button. Let's try that again. What happens if I increase the temperature?
Increase the volume.
The volume's going to increase. How would I know that?
Because they're directly related.
Okay, they're directly related. How do we know that? What happens when I take a hot air balloon and I increase the temperature of the gas? The balloon expands. So it's a physical observation that theoretically you've seen or had some experience with. Could we also use Pivner? Well, yeah. If this temperature gets bigger and everything else stays constant, what has to happen to volume? It also has to get bigger, because that's an equality. That's the whole point of the equality. Make sense? Right. Some of these are more obvious than others. It just kind of changes with each of those systems. Pressure and volume. What happens if you decrease the volume? You are now told to get in a coffin. And we're going to close it up. Don't worry, we won't bury you. You wouldn't know, because we'll start throwing sand on the top of it just to make you feel like we're burying you. What's going to happen to your pressure? It's going to go up. Right? They're indirectly related, or inversely related. Can we see that in the expression? Well, they're on the same side of the equation. So what should we do? We could set the other side constant. I see where you're going with that, and I don't think that's as easy to see, but that's okay. We'll look at yours. You said it. Let's look at yours first. PV equals N, RT are all constant, so it's 1. If the volume goes up, what has to happen to the pressure to make that equation still equal 1? It has to go down. Okay, it has to. Okay? And after now saying that, you're probably right. Yours is actually probably easier. Because I was going to do this. And now that becomes problematic because it's a fraction, and your way was probably better. But we'll still go through it because, of course, I've got it. If the volume goes up, 1 over 1,000 versus 1 over 1. Right? The volume went up. What happened to the pressure? Goes down. Okay? You can see the relationship here. You can also see the relationship here. Okay? Kind of makes sense? You should be able to do that with any of those variables, any 2. Okay? Maybe on this exam, I haven't quite decided, you might have one solve where you have to deal with all of them, and you have to use Pivner. Okay, one question at most. Okay, and arguably all that is just plug and chug. What's the pressure? Put it in. What's the volume? Oh, I don't know what it is. It's X. I don't know what it is. What's the mole? Oh, I plug that in. R. R is one that I arguably won't tell you to memorize. I know I just gave exam 2 back to at least 2 people. Does somebody have that exam to see on the front? Did I give you R? I think I do. Is that?
No, you don't.
Well, that was stupid. I'll put it on the front. I gotta fix that. Okay, so I will give you R because I don't think that's necessary to go through and memorize for this class. Make sense? Okay. Questions? Okay. After that, we encounter Dalton's law of partial pressures. Okay. This really comes out of all those assumptions that we made about gases at the very beginning. Okay. When we said gases don't have a volume. Okay. That's probably the biggest contribution for why we get Dalton's law of partial pressures. If gases don't have a volume, does the volume change when I put more gases in? It shouldn't, because they don't have a volume. Okay? So they will each be exerting on the container their own pressure independent of all the other gases. Okay? They don't care about any other gas because they all have zero volume. So what ends up happening, each of them is going to exert their own pressure, which then means I can just add up all of those pressures to get the total pressure. That's it. Right? And Rose being like, that sounds really easy. It is. That's it. That's all you do. You just add them up. Right? So you would add up the partial pressures of each of the gases, right? And now you have the total pressure within the entire system. And that's because each particle of the gas is exerting a pressure. We have to take into consideration each particle. Okay? Do you want to solve one? I even heard a no. Wow. You said yeah? Oh, okay. Maybe it was psychological. Maybe I was hoping for a no. Okay. So, sample of noble gases: helium, neon, argon, and krypton. One thing I'll state right out of the gate: why would we pick noble gases? They don't react. Okay? Noble gases are an ideal gas. Everything about them is they don't react with things. So they would fit this pattern really, 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 really well. If I'd pick something like water as a gas, well, water is going to be a little bit more problematic because water is polar. It had those partial charges, which means we're going to get some kind of interactions, which means we're going to deviate from ideality. Okay? Regardless of the gas, we're making the assumption they're all ideal, so it doesn't have to be noble gases. I just wanted to point that out. Okay? If the partial pressure of helium is 125 millimeters mercury, neon is 45 millimeters mercury, argon, what is the total pressure of the sample? How many of you know what millimeters mercury is? Okay, I'm going to be a bit of a jerk. You all know what a millimeter is, right? Yeah, it's a distant measurement. So millimeters of mercury means like 1 milliliter, 2 millimeters, 3, 4. So when it says 125 millimeters, that's, like that. There we go.
So it's measuring length.
It's a length. Yeah. Where's that length coming from?
The space that it consumes?
It's coming from the atmospheric pressure.
It's a comparison back to atmospheric pressure. Okay? So it's a barometer. It's the height of the mercury inside a tube. Based off the height in the tube, we can tie that back to the pressure of each of these things. Okay? How many atmospheres is millimeters mercury?
1.
Okay, how many atmospheres is millimeters of mercury? So I just heard 1. So what I believe you're telling me is 1 atmosphere. Wow. Let's just pretend that never happened. 1 atmosphere equals 1 millimeter mercury. Is that what you just told me? Yeah, I don't think that's what it was either. It's totally not. I would probably have to look it up, but I think it's 760 millimeters mercury. None of you knew that. Could you answer the question?
Yeah.
Yeah.
You just add them.
You just add them up. Is it saying that it wants it in atmospheres? No. So what are we making the assumption of?
They just want to keep it in the same unit.
We want to keep it in the same unit. So what should you do? Just add them up. Right? So we would take 125 millimeters of mercury for which one? Helium plus 45 millimeters of mercury for
Neon.
fair enough, plus, oh my gosh, why couldn't I just pick 3 gases? Millimeters of mercury for, now we got argon, plus 17 millimeters mercury krypton. What is the total pressure of the sample? So you added all those numbers up and you got, what was it? 345. There we go. Millimeters of mercury. But wasn't the 17 millimeters of mercury for krypton? Isn't that a different unit than millimeters of mercury for argon? No. The unit is millimeters of mercury. What's the substance? The argon. Is that a different unit?
Yes.
Yes. Am I being a bit of a jerk?
Yes.
Yes. I don't care. Dalton's law says just add them up. Don't worry about the units. Really? I don't have to worry about the units? Yes. Just accept it. All right? So here we go. 345 millimeters of mercury, all the gases. Make sense?
Yes.
Absolute zero, this is kind of a fun little graph. So one of the reasons why the Kelvin scale works for us is we don't have that negative that we would get with degrees Celsius and Fahrenheit, which would invalidate the ideal gas law, or at very least make it insanely messy. Right? So someone went through and started to extrapolate, well, where is my theoretical limit? Right? And that's 0 Kelvin. And what we're assuming at 0 Kelvin is that we now have 0 energy. Okay? I just think this is a fun one to kind of mind game with. What would it mean if we achieved 0 energy? No movement. Do electrons move? Yes, which means they have energy. So what happens to electron movement at absolute zero? It should theoretically stop, like everything stops. Which just seems kind of weird to me. I don't quite understand it. I tried to have a conversation with a physical chemist that understood it better than I did, and I still didn't understand what they were talking about. Right? But absolute zero is our theoretical limit. Right? We can't go negative. That said, as soon as we have these well, you can't do that, of course some scientist out there says, well, you can't tell me what not to do. And somebody has gone through and has kind of computationally generated a temperature that is lower than 0 degrees Kelvin. Right? Which is really, really bizarre and kind of fascinating and neat. They achieved negative kelvins without passing through 0, which is the other kind of weird part. Okay? So just how the system is built and how thermodynamics is designed, they were able to do it. At least theoretically, I have no idea if someone repeated the experiment. Okay? But it was kind of neat. Right? If you get into thermodynamics or further along in chemistry, you're looking for thermodynamics and some kind of high-level thermodynamics to talk about that. And that might be something you should press on a teacher then, because they might be like, what are you talking about? And then you could look it up together and find out that I was wrong. Okay. But I'm pretty sure it happened. So 0 degrees Kelvin is our limit. We can't go lower than that. We can get really, 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 really close to it, but we've never achieved exactly 0 Kelvin. All right. Which takes us back into chapter 9. So now we get kind of a fun concept, and by fun, probably not fun because it's dealing with all our conversions again. All right. The limiting reactant concept. We'll go through and look at examples that are kind of silly. Okay, we looked at bicycles. We looked at we will look at sandwiches. All of these things are trying to get at a macro scale, something larger that you can grab a hold of and you can manipulate. You have to use those same rules down in the micro or nano scale with chemistry. Okay? So if you have 5 slices of cheese and 8 slices of bread, how many sandwiches can you make?
4.
Okay? By shouting out an answer, I'm going to guess you did not use all the rules we've been talking about. Okay? So what I would like you to do is use the rules that we've been talking about. Establish the work to show how many sandwiches you would go through and make. Okay? And I know, that seems silly, but that's what I would like you to do. For those of you that are still like, I don't want to write all that out, this is why we came up with symbols. Cheese, C. Sandwiches, S. Bread, B. Now you don't have to write it all out. You don't like bread as B? Right. Come up with a unit conversion that allows you to get to that answer that you so quickly jumped on for how many sandwiches you could make. And if you got questions, you can raise your hand. I'll come to you. So I know we just had a long weekend, and we've been talking about gases for at least a week, so you're like, I don't have to worry about this conversion. All this is a conversion question. You've internalized a lot of calculations because of that macro scale. Okay? So, again, what you want,
Cheese and bread was on the bottom.
we'll go through it. What you want to do is use that exact same process that we've done for every other conversion question. Okay? We start with what we want. I want sandwiches. What was I given?
Cheese.
5 slices of cheese. Right? Is cheese the same thing as a sandwich? No. So what do you need to do? I need to convert the cheese into sandwiches. So I would put cheese in a denominator. Why?
You want to get rid of it?
I want those units to cancel. What do I want in the numerator? Sandwiches. What is the relationship between cheese and sandwiches? It is 1 to 1. How do I know it's 1 to 1? From the balanced chemical equation. And we can have that debate later about that being an awful sandwich. Okay? But this is just basics. Keep it simple. Okay? Is that the only thing I should be concerned about? How many sandwiches would that equal? That would be 5 sandwiches. But we heard several people shout out the answer. The answer was 4 sandwiches. Well, last time I checked, 5 does not equal 4. So what are we missing? Okay. I also have to take into consideration how much bread was present. Because when I looked at this 5 slice of cheese conversion, I'm making an assumption. What am I assuming in that 5 slice of cheese system?
That you have all the bread.
That I have a ridiculous amount of bread to account for all 5 sandwiches. Okay? So in that first case, I'm assuming bread is in excess. I have more than enough bread. Right? In the next one, what am I going to assume? Okay? I'm going to assume cheese is excess. Well, how much bread did I start with? 8 slices of bread. I want to convert, get rid of the bread unit, and I want my sandwich unit. What's my conversion factor? 1 sandwich is 2 bread. I can now punch that into my calculator, and I get 4 sandwiches. So all of y'all were wrong. I should have gotten 9 sandwiches. 5 plus 4 is 9. What do you mean no? Isn't 5 plus 4 9?
No, you have to go with the smallest one.
Why?
Because that's your limiting factor.
Right?
Limiting reactant.
I can't possibly get 9 sandwiches. I only have 5 slices of cheese. Right? As soon as I hit the 5th sandwich, what happens? Out of cheese. I can't make the other 4. Right? What happens with my bread? I can make up to 4, and then what happens? I don't have any more bread done. Right? So it's not just a question of adding these things together, it's think about what they mean. In this case, that means the most I could get would be the smallest number of my calculation, which ends up being 4 sandwiches. Make sense? Right? So some other words that come in. Number one, we saw excess. Excess has popped up in our previous calculations, and in most of those calculations it's thrown in as in this reagent is in excess, meaning I don't need to worry about it.
Yeah.
Right? So I could rephrase the question that says, if I have 5 slices of cheese and excess bread, how many sandwiches can I make? 5. I immediately go into the cheese. I don't have to worry about the bread because it was in excess. I don't have to do that second calculation. Does that make sense? Right? The other word that comes into this is limiting reactant or limiting reagent. Right? Limiting ingredient. What ingredient prevents me from making more sandwiches? Right? In this case, it's bread. I run out of bread and I can only get 4 sandwiches. So bread is the limiting reagent. Right? When we move to the chemistry side of it, you're doing exactly the same thing. Right? You're establishing those conversion factors, determining how much you could maximally make with the assumption the other one is in excess, and you're then reporting out your answer. Right? There are other variations on the same theme. All of them result in the exact same number of calculations. It just depends what you want to do, right? Or what you're interested in looking at. All right? Kind of make sense? Yes?
Is there a difference between reactant and reagent?
Reactant and reagent mean the same thing. Kind of like purple and violet. Right?
That depends if your favorite color
Not
is
on
purple.
the scale.
Depends on who you ask.
I knew I was walking into dangerous territory there. Okay? For the most part, they're the same. Okay? So, there's our text explaining that. Yep, we get it. So, what happens if we now switch it to this? 2 moles of sodium carbonate are mixed with 2 moles of water and 1 mole of carbon dioxide. How many moles of sodium hydrogen carbonate are produced? Why is this question more challenging? We have 3 different reactants. None of them are listed in excess, which means I have to do each one. So I can start with sodium carbonate with the assumption that I have excess water and excess carbon dioxide. Okay? Make sense? So set it up, solve it. Same thing that you already did. So how do we start? Okay. We're trying to get it converted into moles of sodium hydrogen carbonate. So what do I start with? 2 moles of sodium carbonate. Those the same thing? No, what do? Moles of sodium carbonate. Moles of sodium hydrogen carbonate. I'm going to get a bit sloppy on this because I think a couple people were jumping the gun on something that we need to watch out for. And I think the next question will address that, right? 2 moles sodium hydrogen carbonate, 1 mole sodium carbonate. Where do we find that? Balanced chemical equation, which means how many moles do I get? 4. So now I can go through and do it for the next one, where I want moles, again, sodium hydrogen carbonate, starting with 2 moles of water. Moles water, moles sodium hydrogen carbonate, yeah? Ratio 2 to 1, right? What do we get? 4. But we got the same number. I think I even heard somebody say that. Good job. That was kind of the point. Maybe. Last one, moles sodium hydrogen carbonate, starting with 1 mole of carbon dioxide. How do I do it? Mole carbon dioxide, mole sodium hydrogen carbonate, right? 2, 1. The answer is 2. So what's the amount of sodium hydrogen carbonate produced? 2 moles. It's our smallest number, right? The end. So we're now comparing these to each other. What is the relationship? That's the smallest one. What is our limiting reactant? Carbon dioxide. What is our reagent in excess? Water and sodium carbonate. Okay? Kind of makes sense? Okay, so I want to address 2 things out of this. Number 1, question came up of, do I have to show all this work? Depends. What does it depend on? Is it a show your work question? If it is a show your work question, yes, unfortunately you have to show all of that work. It didn't take that long to write out. You can write all that work down. Okay? If you wanted to with the show your work, you could do it in your head and say, this is the answer, and then you could even write, if I have time, I'll come back and prove it to you. Okay? And then go on with the rest of the test. Okay? Make sense? Okay. The next part on it, is there a shortcut? Does anybody see something that you're like, oh, couldn't I just said that? What do you got?
You only have 1 mole of carbon dioxide, and if you look at the coefficients of everything on all the reagents, they're all also 1. So you can basically, they need to be equal to produce your.
So I know where you're going with that. So let's see if we can step back away from that, because that actually involves an extra interpretation.
And just look at the equations, there are only 2 moles of sodium hydrogen carbonate.
You can't just look at the equation, right? And so that's, and here's why you can't just look at the equation. Can I just look at the equation to say only 2 moles of sodium hydrogen carbonate are produced?
No.
If I start with 1 mole of everything else, then fine. But what if I started with 1/3, a mole of one, and 0.6 of another, and 0.2 of another? That wouldn't work out. Okay? So I think I know where you're potentially going with that. And you're using the equation and you're using the given information and lining them up. Okay? Which is exactly what you were doing. Okay? So you internalized a lot of those calculations. And when you internalize those calculations, when you do it right, it's okay. This version of the question, I would argue, is probably not going to show up in a show your work. Because some people are good enough that they could do all of this in their head. And I don't want to penalize people that have done enough practice to recognize how to do that fast. So that version, this version of it, would get dumped into a multiple choice situation. Okay? For those people that weren't comfortable with it, they'd still have to go through all that work. They'd still get to the same answer. Does that kind of make sense? Okay. Come on. Interestingly enough, neither of you actually said the answer that I was half expecting to see. Isn't 1 smaller than 2?
Yes.
So can I just say 1 mole of carbon dioxide is my limiting reagent? Did anybody see that and go, that's what I want to do? Right? So what we're saying in that case is that I'm now ignoring the equation and just saying, well, 1 is smaller, that's my limiting reactant. That is an insanely dangerous thing to do. Hopefully I did this one right. Okay, given a half a mole, 1.5 moles of hydrogen and 1 mole of oxygen, how much water can you make? Okay, so, man, did I do the freaking wrong one again? We'll just see. I may have to switch numbers around. This is so for those of you being like, people who just come up with questions so fast. I just came up with this question so fast, and I'm pretty sure I came up with it the wrong way that I wanted it. Okay, so let's just see what would happen. Okay, how much water can you go through and make? So, water, and in theory, moles. Starting with 1.5 moles of hydrogen. I need to do my conversion. Moles of hydrogen to moles of water, right? Yep. Where's that conversion factor? Okay, good. A lot of people shouted that out. You have to balance the equation first. The equation isn't valid yet. So to balance it, 2 and 2. Oh, maybe I did it right. So 2 and 2, and I would get how many moles of water? Try that. You're right. You can. No, you're not. 2 and 2.
Oh, that's 1.
1.5. It's that selective vision thing. Got to watch out for it. Moles of water and moles of oxygen, right? What did I start with moles of oxygen? 1. We can already say, like, I screwed this up, right? The 1 is smaller than 1.5. That clearly has to be the answer. So we go through. Oh, did I do it right? Moles of oxygen needs to cancel. Moles of water, right? What's our ratio? 2 to 1. And I would get how many moles? 2 moles. Water. Which one's our limiting reagent? Hydrogen is our limiting reagent. Was 1.5 smaller than 1? No. You have to take into consideration the balanced equation. For those of you that could take into consideration the balanced equation, that's fantastic, that's phenomenal, you're awesome, you're better than the rest of us, that's cool. Okay? On a show your work, arguably what we would go through and do is pick numbers that weren't as easy to manipulate, 0.423. And 0.6, why not? 513, I don't know. Okay, does that make sense? Now you wouldn't be able to internalize that calculation quite as quickly. You would need to write it out. Does that make sense? So a lot of the examples we talk about in class are intended to minimize that calculator work. Okay, when it gets to the exam, you do have to show that calculator work, particularly in a show your work situation. For those of you who are like, I could do this in my head, could you still do this one in your head with those weird numbers? You're just saying that to spite me. Okay? So the intent is to recognize that extra work. Okay? The next thing that I want to throw on there, let's switch back to those regular numbers. Okay? On a multiple choice, any guesses what your answers might be? 1.5 moles. I'm going to bet a 1.0 moles. I'm going to bet a 2.0 moles, assuming sig figs, which I didn't even interpret potentially for this. Just because you said it over there, 3 moles. Aye. And yeah, why not? Anybody see a problem with just punching numbers into the calculator? Right? All of those answers are potential possibilities. Does that make sense? So a test that's written well, which theoretically I do, right? You can't just randomly punch numbers into a calculator. If that's what you feel you were doing, I'm like, I think I'm just randomly punching. Stop punching it and just guess. Okay? Because you will find a numerical value that matches what you're punching in the calculator. Have some reasoning behind it. That's what this work is for. Good? Okay. So, percent yields. Okay? You, in theory, already did a percent yield. Technically, it was a percent recovery in lab last week. Because everybody had lab last week, right? Yeah, just checking. Okay. You had the copper ore lab, right?
Yeah.
You went through and did it. How much ore did you recover? Anybody want to volunteer? How much copper?
I think it's like 60%.
I didn't ask for percent yield. How much copper did you recover? 0. Point what? 249. I did that experiment and I got 5 grams. Whose ore should we mine? Mine? Really?
Actually, no. We don't know.
We don't know. Why do we not know?
We don't know how much
Mass
we...
was taken.
Yeah.
What's that?
I got my 5 grams when I developed or moved through 500 grams of ore. Okay? You did it when you got 1 gram of ore. right? Ballpark? Okay. So we have to come up with a way to standardize those results so we can make a fair comparison. That's the point of a percent yield. It's a way to standardize it so that when we report out our answers, people can be like, oh, that's really good. Okay? The same thing would happen in a class. You want to be able to report out a percent on the test. Okay? Otherwise, you're making some assumptions. Like some people are like, oh, I got 100. I did really well on the test. It was out of 200. Not so hot. Okay? So we have to have a way to standardize those results. That's the point of a percent yield. Okay? That standardization, take what you actually obtained or what you scored and divide it by the maximum possible. Okay? Your theoretical. In the case of your lab, the copper ore lab, you're making the assumption that the entire dirt sample you got, all of it was copper. Okay? You probably would have known that, before dissolving it in acid and all that other fun stuff, right? Theoretically, you would have been just like, dude, this is just copper. You should go mine this. Okay? But we may not necessarily know that. Okay? So we have to make that kind of initial assessment. Okay? What are the units on the percent yield? Okay, this one's a little bit trickier. Okay, well, let's use the copper lab. Well, yeah, let's just pretend that didn't happen. Twice? 3 times? How many times did I push the button? And it's locked up. Perfect timing. Wow, everything's... Oh, okay. Well. Seriously? What is going on? Percent copper, right? You had an actual over theoretical. What were the units on your actual? Always leave off that stupid 100%. What was your actual? I disagree. Grams. Grams of copper. What was your theoretical? Grams of copper. Okay? And some of you may have been like, well, the theoretical wasn't grams of copper, it was the mass that I started with. Theoretically, the mass that you started with was all copper. So when we're doing a percent yield, what happens to the units? They cancel out. When should they cancel out? Every single time. Whenever you do a percent yield, those units had better cancel. If they don't cancel, something's wrong. Like my computer. Okay? So we have to be careful to make sure that our units cancel. So if we took a look at, because I think that's all I wanted there, this question. 2 moles of sodium carbonate are mixed with 2 moles of water, 1 mole of carbon dioxide, and, notice the and, more information, only 0.5 moles of sodium hydrogen carbonate are produced. Then what is the yield of sodium hydrogen carbonate? Okay, so if we set this up, what are we being asked to solve for? How are we going to solve that? What do we need? The actual, because I make you write units, I'll go through and write it too. Actual sodium hydrogen carbonate over. Am I given those values? Which of those values am I given? Because I heard it.
The actual 0.5 moles.
We are told that you obtain 0.5 moles of sodium hydrogen carbonate. Okay. This isn't actual yield. This is what was obtained in this experiment. Okay. Do we have the theoretical?
Yes, you have to figure it out, but you do.
Right. So I'm not directly given it. I would have to figure it out. How would I figure out the theoretical?
You'd have to find out what your limiting factor is.
right? Because I've given all of those starting materials, I would have to take 2 moles of sodium carbonate and try and convert that into moles sodium hydrogen carbonate. How do I do that? I would need a balanced chemical equation. Do I have that? Yeah. Moles of sodium carbonate, moles of sodium hydrogen carbonate. The ratio according to the equation is 2 to 1. So it would say I would get 4 moles of sodium hydrogen carbonate. This starts to sound kind of familiar.
So that's our theoretical.
Careful.
No, because we still have 2 other.
We have 2 other reactants that we would have to check. This is a possible theoretical. I could possibly attain this as a maximum if
Everything is in excess.
all the other reagents were in excess. Are all the other reagents in excess? Well, to figure that out, what do I have to do? 2 moles of water. How many moles of sodium hydrogen carbonate? Yeah? Is this looking familiar yet?
Yeah.
Why is it familiar?
Because we just did it.
Okay, good. We just did it. So you can tell me what all those numbers were, right? 2 moles water, moles sodium hydrogen carbonate. We got 4 again. And if we go through and do it with our 1 mole of CO2 equals 2 moles of sodium hydrogen carbonate. Yeah? What's our limiting reactant? Carbon dioxide. So to calculate this, I would just take 0.5 moles of sodium hydrogen carbonate, and I would divide by my limiting reactant, 1 mole CO2. No, why not?
Because you want the units to be the same.
The units have to be the same. So you've identified some important information. CO2 is the limiting reactant, but that doesn't allow me to do my unit conversion. What does that mole have to be in for the theoretical?
The sodium hydrogen carbonate.
The moles of the sodium hydrogen carbonate, which I calculated down here, which numerically was 2. So 0.5 divided by 2 times 100%, 25%? Got it? Okay, which part of my handwriting are you making fun of now?
Love to.
Which one?
The second one.
That? Yeah, I can see that being confusing.
It's a fish.
Is that better? Now we're from our balanced equation. Make sense? Okay.
So we want 5% yield or 4% yield?
So there's an interesting question which technically is outside the scope of this class, okay, or the lecture. Right? That's really reserved for the lab. So the question was, what kind of a percent yield do we want? Do we want a high percent yield or a low percent yield? I calculate the percent yield of a toxic gas coming out of my power plant. What kind of yield do I want? I want a really low percent yield. I don't want toxic gases coming out of my power plant. Okay, they should be trapped by all the scrubbers that clean them. Okay, I'm looking at the percent yield for copper in my ore sample. What kind of percent yield do I want? High. Right? What is a high yield?
Better.
It depends on
Well, it depends entirely on the situation that you're looking at. Okay? So in a chemistry lab situation, typically what happens is that you would look at a literature result, right? And you would compare yourself to the literature. If you made big alterations from the literature, you might be like, well, cool, I got a better yield, now I can publish my result. Right? You can also look at it and be like, wow, my yield was really crappy in comparison to theirs. Right?
They just keep doing it their way.
I could switch back to doing it their way. So we would use that context. What if nobody's discovered it yet?
Then you got the next one.
You theoretically have the best one, but you have to prove it. Right? And you will have to prove it by doing, we still got time, prove it by doing repeated experiments. and you would average your results, theoretically average your results, but probably what would happen is you would ignore the first time you did it, because what happens the first time you did it? Okay? This is the first time taking this class. Would, theoretically, okay? Would you base a published result based off of your grade in this class?
Yeah.
Some of you are like, God, no, I don't want anybody to know my grade. Because it's your first time taking it. The first time doing anything, you suck at it. Okay? With practice, you can improve. So for publishing those results, you're probably looking at running the experiment tens of times. And theoretically, what you would pick would be the last 3 or 4 times you did it and average those as a percent yield. You wouldn't average the initial ones, because the initial ones are likely wrong because, well, they were a trial. Okay? So it really depends on the system that you're looking at. Let's see, am I actually connected? No, I'm not connected. Can I get just one more slide? Please, just give me one slide, you stupid computer. There we go. Hey, and now we're connected again. So, limiting reactant and percent yield concept. This question is fair game for your extra credit. 50.6 gram sample of magnesium hydroxide reacted, yada, 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 yada. Percent yield, you need actual over theoretical. You should notice that we do have an actual in here, but we don't have a theoretical. We'd have to run the calculations. The calculations we ran up here were simple. They were just mole-mole conversions. Is this one just a mole-mole conversion? No. Okay? So this question is really good practice, because what this is going to have you do, what are the formulas for magnesium hydroxide and hydrochloric acid? What type of reaction? What products were yielded? Balance the equation. What's the maximum yield of magnesium hydroxide? What's the limiting reagent? What's the maximum yield of okay? You've got a lot of individual steps. This one question covers everything we've done in this unit and in Unit 2. Okay? I would highly encourage you to practice this. I will not solve it in class. What we will do on Thursday, because there was an all-man, maybe I'll do it on Thursday after we do empirical formulas and molecular formulas, which is the end of the new material, and we should be ready for the exam on Thursday. Tuesday. I was just testing. It's next Tuesday.
Tuesday after?
No, that's I think the final.